Okay, so we are at the second part of day 5, and the plenary speaker today is Zoltan Szabo from Princeton University, and he will talk on knot Floer homology and Kauffman states.
Many thanks for the invitation. It's an honor to speak here. I hope you can all see my screen, but let me know if there is any issue. I will talk about some kind of overview of knot Floer homology and its relationship with Kauffman state. And I will also discuss a few open problems that are related and some progress on computations. So this is going to be a joint work with Peter Oswald, seem to have some difficulty, but hopefully it will be fine. So we'll talk about knot Floer homology, Kauffman states, bordered algebras, and if time permitted, also I try to talk about some more recent ways of computing knot Floer homology. But let me just start. So the main idea is that we want to study an invariant for knots, why this can be set up more generally for knots in an arbitrary C-manifold. We are really, in this lecture, going to talk about the case of the classical knot in S3. And this is already interesting, and it's slightly easier to discuss. And this is the version that has relationship with Kauffman state. So as it turns out, this has different versions. We will mostly use mod2 coefficients, but you could see that the most complicated version of this is really corresponds to actual homology of a chain complex in 2 variables. You can change z to z mod 2, but there are still 2 variables. And you can then specify this, making one of them 0 or both of them 0. And there is also a version where u times v equal to 0. There are different kind of problems. How computable are these? And the simplest for this, I think, is already interesting. And this is the version when you take both of these variables to be 0. And this is sort of the classical version of knot Floer homology. But there are other versions, and we can take one of, there is also a symmetry between u and v. We can make u to be 0, v to be 0. At any rate, it's going to give you a more complicated version, which is called HFK minus. And at some point, I might talk about computational methods. And in this case, in these computational methods, there will be some algebras appearing, which you can see in these papers. And there is also another version, which is sort of an intermediate between the simpler ones and the most complicated ones. This is this u times v equal to 0 version. You divide this ring with this relation. And turns out that is also computable, and I will say something about that later in the lecture. And there is also the most complicated version, which at the moment we don't have a very effective way of computing, and this is where some of the most recent approaches like the Pong algebra comes in to make a computation for these. However, I thought it would be better to just talk about more generally about these invariants, what they are good for, and what kind of questions we can ask for them. So the simplest one is a bigraded homology theory. You can see here a slightly different notation. You have 2 gradings, I and j. I is sometimes called the Alexander grading, and the other one is called the Maslov grading. there is a chain complex, and will be this chain complex that will be generated by Kauffman states, which I will explain soon. And the differential preserves the Alexander grading, the first grading, and decreases the second grading by 1. So what this invariant is good for? So first of all, you can view it as taking ranks. You can take it as a 2-variable polynomial, but it's really more complicated than that because there are homology groups behind that. But if you do that, then you have a 2-variable polynomial, which you can specify by this expression, just basically taking the Euler characteristic for each I. As I mentioned, fixing I, you already have a chain complex. So the original chain complex is the FK hat decomposes to Z different summands. But if you take the Euler characteristic in each and multiply the T to the I, then you get a classical invariant, which is the Alexander polynomial. So that in itself is not too interesting. The more interesting question is how much more information this invariant contains beyond the classical Alexander polynomial. So as it turns out, it does contain more information. For example, you can use these invariants to compute the cipher genus of the knot. This is by looking at this. So this is actually a theorem that when you take the maximal I for which at least one of these homology groups are not 0, then this is the same as the genus of the knot. So that also means that if a knot is non-trivial, then its knot Floer homology group will be also different from the knot Floer homology group of the unknot. And there is also another question of what, okay, so I could fix the genus and I could make I to be the genus of the knot, and then I still have these homology groups which I could add up. And turns out the total rank of that is 1 if and only if the knot is fibered. This, the special case of genus equal to 1 is due to Gini, and the general case to Gini, András Juhász has another alternative proof of the same result. And so, I mean, there are more questions about this invariant. For example, what is the relationship with the fundamental group of the knot complement, and more generally, what kind of geometric information it contains. But you can also look at what happens when I'm trying to look at the more complicated package. For example, allowing it to be a polynomial ring in U, making V equal to 0. And one of the things that was discovered early on in the study of knot Floer homology, this is due to Jake Rasmussen and independently Peter Oswald and I. By the way, I should have mentioned that knot Floer homology itself was discovered by Jake Rasmussen and independently by Peter Oswald and I. At any rate, so you can use, you can get an integer valued invariant out of knot Floer homology that has some relationship with the four-ball genus, gives you an inequality, and sometimes this is sharp, and you can prove statements about the four-ball genus, but not always, of course. And I mentioned that there are more complicated versions of knot Floer homology. By the way, if you have any questions, you can ask me now. I do have a question. Can anybody hear me?
Yes.
Yeah,
Yes.
definitely.
Great, thank you.
We can hear
Fantastic.
you.
Because otherwise, I have the feeling I'm just talking to.
I know, it's like throwing
Open.
stones into
Yeah.
a well.
Fantastic. So moving on, knot Floer homology is closely related to a three-manifold invariant called Hegel-Floer homology. In fact, the way we discovered it was to play with the original Hegel-Floer homology construction and trying to understand the surgery problems of what happens when I take a knot and do, for example, zero surgery on it. And very quickly that leads to this other invariant knot Floer homology. But of course, because of this relationship, there are strongly connections between knot phrenology and Hegel phrenology for surgeries on the knot. And in fact, there are some results on how to use this to compute explicitly the Hegel phrenology of the Dane surgery when you do P over Q Dane surgery. And if you want the simplest version of Hegel phrenology, then you do need this U times V equal to 0 version. But if you want the full package of knot phrenology, then you actually need the full package of knot phrenology. So that is one reason why it's still an interesting problem of trying to make computations for the general case, because that would be also a computation for the plus version of Hegel phrenology. But how to really do this in practice and what is really the construction? There are different, by now there are different ways to do this. The original construction uses just two-pointed Hegel diagrams, which I will explain. But there are other approaches that have been discovered since then, and if your knot is not too large, and in practice you can use a different combinatorial construction due to Manuel's, Gojbat, and Sarkar, called grid homology and grid diagrams, which is a really nice combinatorial approach. But what really happens is that in the definition and the computation for knot phrenology or Hegel phrenology, you can use all kinds of Hegel diagrams. But if you really specify the kind of Hegel diagrams, then you end up with a more, I guess, combinatorial word. And this is what we are going to discuss today. We are going to use knot projections to say something intelligent about knot invariant. So to that effect, this is the running example, although we have slightly more complicated examples as well. I have a knot, a classical knot in S3, and we are going to put a marked edge somewhere. And for that data, we can associate gene. So if you have n crossings, then actually a genus n+1 surface, in this case, genus 4. In this case, we view this R3 plus one more point, so the knot is really in S3, and we are going to get a Hegel decomposition of actually the ambient C-manifold, in this case S3. So we are going to have here a genus 4 Hegel decomposition of S3, but a decomposition with some extra data that will be sufficient to recover the knot. The picture on the right is actually should give you a hint of how to do this for an arbitrary knot. You take the knot projection and you make it singular. So you look at the crossings, you have these 3 crossings, and take a neighborhood, an epsilon neighborhood of that, which will be a solid solid handle body. Then this is the boundary of that is a genus G surface, in this case 4. But on top of that, we are also going to get 2 kinds of circles in this picture. And always we have exactly G circles if the Hegel genus is G. In this case, 4 circles of type alpha and 4 circles of type beta. The way to construct them is that we actually will use this marked edge, and this gives us 2 regions. In general, you have n+2 regions, and you're going to choose one of them. In this case, this is the region, the infinite region. And for every other region, you are going to introduce a contour. So basically just going around these remaining circles. And that would be the alpha circles. And we'll also have exactly as many special beta circles as crossings, and one more. The last one is easier to understand. This is going to be a meridional circle, like here, this is called beta 4 in the picture. And for the crossings, turns out there are two types of crossing, and of course we would like to know which knot we are talking about. But the crossing type gives you this information of how to draw this kind of circle in the around the crossings. And that is giving you something that's called a two-pointed Hagar diagram, which we can try to formalize what it is in general. So you need a genus G surface, and you need two sets of circles, the alpha and beta circles, that they have to satisfy some properties in general. The properties are that they are disjoint from each other, so this is one property, and they're also linearly independent in the first homology. That equivalently translates to the fact that if I would delete the blue circles, then the rest of this genus G surface here will still be connected. So this is like one set of so-called attaching circles, and other set of attaching circles are the alpha circles, which have the same property. So they are disjoint. The red circles are disjoint from each other, but the alpha and beta circles are not. And in fact, the intersection points between these circles will give us the generator of a chain complex. So and actually uses some constructions in symplectic geometry, in particular from Lagrange and Floer homology. Let's just discuss these various objects because they will be relevant. So the genus G surface, it's a complex surface, so you can fix a complex structure on that. That actually gives us a complex. Yes.
Sorry for interrupting. Somebody asks if you could show the 30-second slide again.
The 30-second slide again. Sure. That was the 30-second slide. I mentioned that we are using node projections and that they are different variants. If somebody asks for the PDF file, I would be happy to send them after the talk.
That would be great if you could send it to us.
Yeah, sure.
Fantastic.
Okay, so just discussing a little bit more, just to explain what's going on. Certainly, if I have a picture like that, node projection, I could construct something like this, which we just did that. I maybe also should try to explain that this construction is a little bit more general. If I have all of these things and these extra 2 points, which I forgot to mention, these W and Z points, then there is always going to be a three-manifold associated to it. The way to construct the three-manifold is to take the genus G surface and attach disks to them, two handles, and this will be corresponding to the alpha and the beta circles. So for each alpha circle, I could fit in a disk, and that actually determines a handle body. In the case at question, the handle body that you are going to construct out of, say, the red data will be the outside of this solid handle body, which is also handle body because we added the point at infinity in S3. And for the blue one, we'll get the solid handle body that you can see, which is basically some epsilon neighborhood of this picture. But there is also a chain complex associated to that. And the chain complex will use the intersection of this T alpha and T beta torides. So the symmetric product of the surface is choosing G points, but unordered, so arbitrary. I can use the same point more than once. But I'm not going to distinguish the first and the second and so forth points. So we are taking the G-fold product of sigma G with itself and dividing the symmetric group on G letters. Inside, there are two half-dimensional torides. These are called T alpha and T beta, which are, when I specify that one coordinate among the G has to be in alpha 1, another in alpha 2, and so forth. And that the base points that we have give us complex codimensional one subpart, and I specify that one of the points is Z, and otherwise I specify one of the points is W. And in the intersection of these two tori, will be so these are half-dimensional, and in general they intersect each other transversely. You can see from the picture that the intersection of the red and blue curves being transversal translates to these two tori being transversal. And then there is a chain complex when the generators are these, and the holomorphic, and then the boundary maps actually correspond to holomorphic disks donating these generators. So these are holomorphic disks with some boundary constraints. One part of the boundary lies on T alpha, another part of the boundary lies on T beta. And at the intersection, you have two generators, and there are various other things like these moduli spaces of disk have Maslov indexes, and you're only counting the case when the Maslov index is 1 and dividing with some reparametrization action. So this is actually a much more complicated story than we would have time to go into, but let me start with the good news. So I guess one remark is that the 2 points are really important in general, because you can use these 2 points to recover the knot. In the case at question, the way to do that is to connect the 2 points in the complement of the blue circles, which will be some kind of curve on the surface, and push it into the red handle body, which is pushed it out in the complement of the knot. And there is another arc when I connect Z and W in the complement of the red things, which is going to be just a short arc, which at the end, if you really follow that recipe, will just give you back the knot. In general, it will give you a knot in the corresponding 3 manifold, but in this case, this is designed exactly so that we would get back the original knot. And this is a specification of a more general construction, but a specification when we can really understand combinatorially something about what's going on, especially we can understand the generators. So for example, in this picture, you could see I have to choose 4 points, but I have to choose it in the intersection of T alpha and T beta, which means that I could look at the coordinates of the points in the surface, which means that since beta 4 intersect only one of the red circles, I have to choose this coordinate, which I'm pointing at. And on the other 3 crossing, I have choices. Each of the crossing corresponds to one blue circle, and that intersect the red things in the corners. So I have to choose a corner, and I have to do that consistently so that every circle gets exactly one corner, and that would be meaning in the intersection of T alpha and T beta. And turns out this is something combinatorial that Kauffman already studied when writing down the Kauffman states for the Alexander polynomial. So in this language, what we are really doing is taking the knot projection, choosing a special arc here, which is also relevant in the construction of the original Kauffman states. And all we do is just to try to look at where this intersection between T alpha and T beta lies, and that we can denote by this dot, which will be exactly one of these Kauffman corners. And we get exactly the same condition as Kauffman associated to these pictures, which is that I have n+2 regions originally, if I have n crossings, but I choose 2 of these regions specially next to this marked edge. And I have n remaining regions, and I also have exactly n crossings. At each crossing, I have to choose one of these corners, so that each region and each corner gets exactly one dot. And that is a finite combinatorial picture, which is all the Kauffman states for the projection. And what Kauffman does is to give a state sum formula for the Alexander polynomial using Kauffman states. We have a very similar story. Knot-Floer homology is a bi-graded theory. It has an Alexander grading and a Maslov grading. So we have to associate, instead of one number and the sign, we have to associate two integers. And that's actually not that hard to work that out. So one could use the original definition of knot homology that works for general two-pointed Hegel diagrams and just write down the corresponding state sum formula for both gradings. So you can see here positive or negative crossings. We have 4 kinds of corners around them. And these will be the T powers of what you see here for the Alexander grading. And if I would just have the Mostow grading mode 2, just 1, 0, 0, 0, that would be exactly giving you the sign that associated to the Alexander polynomial state sum formula. But here we actually need integers. So this is a slight modification of the original construction. And what it does is giving you bi-gradings for all Kauffman states. Now, the differentials are a bit tricky, but if you want the simplest u equal to v equal to 0 version, then the Alexander gradings are fixed. The Mostow gradings in the boundary map decreases by 1. It's a chain complex. You can take homology, and the homology of that chain complex is not Floer homology. So the first question is, how can we use this knowledge to actually make some calculations of not Floer homology? I mentioned that in general, this might be hard because in the general definition, we have to actually compute a holomorphic geometric problem, giving 2 intersection points between these 2 Lagrangians, try to find the holomorphic disks connecting them. Holomorphic disk with some property, and this property actually comes in the use of the base points. There are all kinds of holomorphic disks, but you can intersect them with these base points or the corresponding complex codimension 1 subvarieties. And you can ask that these intersections are 0, for example, and that would be the u equal to v equal to 0 version. Or you can ask them to be a specified number going through w or z in a certain number of times. And that would be the general ZUV version, when u, say, correspond to how many times intersect w, and v would correspond how many times intersect the other base point. The good news is that this being holomorphic, the intersection will also be greater than or equal to 0, so you don't get negative intersection. The other good news is that we can understand these intersection numbers. You can use other reference points. For example, around each of these edges, you can use 2 reference points above and below the blackboard. So something that lies a little bit above the blackboard and something that lies between below the blackboard, and also this will use some 2 numbers associated to this homotopy class of topological disconnecting 2 generators. So turns out of not doing any real work, just these Hegel diagrams, one could get really strong computations in special cases. So the special cases are when the knot is alternating. And this is a theorem that one could prove early on, that if the knot is alternating, that all the differentials in the knot-Floer complex, this to u equal to v equal to 0 version, vanish. And the reason is, actually, if you go back a little bit and unpack these kind of state sum formulas that appear here, what you could see is that all the generators lie in a special line in the bi-grading, and in particular, there is no room for differential. So it's not just that we can immediately compute the knot-Floer homology. The total rank of the knot-Floer homology for an alternative one would be exactly how many Kauffman states it has in the alternating projection, but that we can also just compute the bi-graded homology, and it uses just the Alexander polynomial signature, so it is still for alternating knots. It's sort of a letdown. You don't get many new interesting things. But as it turns out, for general knots, you can prove much stronger results, and you can prove the relationship with the genus and so forth. But what if you just wanted to know the answers? So I give you a knot, which is, if it's alternating, fantastic. You can immediately compute this knot for homology. But what can you do in general? So it turns out there is a simple trick which we have time to discuss. That for special families of not too complicated knots, for example, pretzel knots or Kinishta-Terasu and Conway knots, you can still use some, at least in some Alexander grading, you can compute the knot Floer homology, and you can get some interesting information about genuses of certain knots with this technique. So let me try to explain that, because that not contains any complicated holomorphic geometry. So the main strategy used early on is something really simple. We know that this is an invariant, or we prove that this is actually invariant. So can just fix an Alexander grading that you are interested in, that try to compute the knot Floer homology for those Alexander gradings. You can choose your favorite knot projection, hopefully with only a few Kauffman states in that grading. And you can also compute some information about the relative homology classes of connecting these generators. And if you got really lucky, you can compute the moduli spaces as well. And then this is the answer. And if you are unlucky, then you can try to persist and try to get a different projection. So this is a very simple approach. Turns out in some cases works very well. In fact, for some infinite families, it works really nicely and gets interesting results. And if that's okay, I would like to discuss a little bit this case, which is one of the Kinishta-Terasaka knots. It's actually not the simplest Kinishta-Terasaka knot. The simplest one will have just 3 crossings here and 2 here and 2 here and 3 here. But you can see this comes in a family. It's actually a 2-parameter family you can make, and this R+1, R+1. So you can change R. You can also change these crossings to be some even number. Here it's just 2. So what you see here demonstrated is that we fix one Alexander grading. Usually the computations are easier when the absolute value of the Alexander grading is large. If it's really large, usually I can just immediately see that the homology is trivial because no generators whatsoever. But here in Alexander grading -3 for this example, you have actually exactly 2 generators. So one is the black dot gives one kind of Kauffman states with Maslow grading -2, and the white one gives you an Alexander grading with Maslow grading -3. And there is a topological disk between them because they are in the same Alexander grading. And this topological disk does have Maslow grading 1. So there is no sort of immediate way of discarding this example. However, when you compute the homotopy class of the disk connecting them, and turns out it's a very simple algorithm, which you can more or less guess from this picture, the coefficients around the marked edge will always be 0 for both above the blackboard and below the blackboard. These are the 0, 0. And however, that kind of numbers eventually could change, and they will change exactly when you go through the knot. There is a point when the 2 kinds of Kauffman states on both sides of this line, and this changes by either +1 or -1. And okay, so there's a simple rule which you can actually compute the gradings everywhere. And eventually, when you come back to this part, it will become 0, 0. And of course, it has to be because they are the same Alexander grading. However, what you could observe that some of these numbers in these examples are negative. It means that the disks that we are studying will have negative coefficients around these regions, which means that since it's holomorphic, it just cannot exist. So this is this positivity of intersection with complex things that we are using here. And so it means that we have 2 generators but node is connecting them. And so the differential is 0, which means that we can compute the node Floer homology in Alexander degree -3. There's a symmetry that also computes it for 3. So turns out that is already useful, but of course, it is really going to be always a partial computation. For very small crossing knots, you can actually make that work, but for general knots, this is not going to be sufficient. And that brings up the two obvious questions. So one, I think it's very interesting, and in its full generality, it's still not answered. So this is, suppose, so we know what node Floer homology does. For any node projection, you have a chain complex, which is generated by Kauffman states. You know the bigrading. All you need to do to solve this problem is to come up with your own definition of what is the boundary map between Kauffman states, preferably satisfying some property. So you do certainly want a chain complex. You want the Kauffman state to satisfy the bigrading formula, because we know that's true for node Floer homology. And of course, you want not just this a chain complex for a given projection, but you want invariance on the Rademacher moves. And that would already be interesting. Of course, if you want to aim for something that could possibly actually isomorphic to node Floer homology, you want more, at least for some examples, you want the same answers. Or you can ask for on-node detector, computing the genus and detecting fiber knots, for example. So in its full glory for the full node Floer homology, this is unsolved. Really combinatorial in the usual sense of just using the node projection and nothing else. It is still an open problem, which I'm very interested to study more. But in some sense, if you are willing to not just use the node projection, but give some extra data, like, for example, fixing the y coordinate in the node projection, then one could actually make some advance, and I will talk a little bit about that. But the other problem is just computation. So we know that there is a node Floer homology. We know there is a chain complex. Can you just somehow compute that chain complex one way or another? And turns out the second problem, now we know how to solve, and I'm going to talk about this a little bit, at least in the u equal to v equal to 0 case, or the u times v equal to 0 case as well. So what is the computation? One difficulty in the original problem, and of course, talking about reverse engineering, there is a whole complex geometric problem. So one approach should be just try to solve that. The difficulty with this is that the boundary map actually depends on the complex structure you put on the surface. And it's not, unless you just somehow encode that, then you don't expect then there should be a nice answer. And one way to try to encode that is to look at a special degeneration of the complex structure. There is the node, there is a G-energy surface around that, and you can try to degenerate the complex structure. You can try to generate the complex structure along like one line like this, which intersect the surface at a certain number of circles, or lots of lines like this. At the end, we did use lots of lines. But if you just use one line, then you decompose the node projection into two parts, the upper and the lower parts. And somehow combinatorically, you can think about what you are really trying to do is understand, first of all the Kauffman state in the projection. But in order to do that, you first have to look at what are the possible Kauffman state in the upper projection. That is something combinatorial called upper Kauffman states. Here you can see an example of upper Kauffman states. You have to use some corner at each crossing. And So you are sort of ready to choose the other Kauffman states coming from below, but you don't know what the below diagram is. So you don't even know where this region will be that doesn't have a Kauffman state. So you do what you can, which is that you set up this combinatorial problem of what are the Kauffman states above and how they intersect the remaining finite regions that may need also Kauffman states. These are extra information of what are the regions that need Kauffman states. So long story short, you can also look at the corresponding intersection numbers we talked about, and this is also relevant. You have some reference points and you try to understand how many times your disk will go through these points. These were with these 1 zeros or -2, -1s in the previous pictures that appear a lot of times. And okay, so we don't have that much time to talk about the algebra, but as it turns out, the Kauffman states and these kind of homotopy classes that you have to encode lead you to an algebra which you can quotient out with some other relations that I'm not going to go into right now. But the bottom line is that you do get an algebra. The algebra will depend on basically how many times your line intersected the projection. So you are somewhere trying to get half of your node projection. So your line, say y equal to t line intersect the node at certain even number of points. In this case, that is 12. And you get an algebra. Turns out there are related other algebras that make sense even if this number is odd. And we worked out these algebras. And the point is that as a computational gadget, you start at the top of the projection and try to see what happens when you increase your diagram. For example, you introduce a crossing. So think about this as a scanner. You have the node projection. You take the y equal to t line, and t is very positive. Then above the t line, there is nothing. But you can lower t and see what happens. And turns out at the end, you can set up a really algebraic gadget that just uses these node projections, plotted extra information about like fixing the y coordinate on the xy plane, and making sure that your projection is sort of in general position with that. And then you can actually do something almost like the first reverse engineering question, but with an extra data. And you do get a bigraded invariant, which is a chain complex on the Kauffman states. And you can even prove that, that if you change the node projection, you get the same invariant. And at least it's a partial solution for that first problem. Maybe I'm not going to go into these parts a lot. But you can, turns out, do various other things. You can work this out over a sine. And at the end, in a separate paper, we looked at the case of, okay, so what's going on when you actually want to prove that this combinatorial thing is really not Floer homology. At least over Z mod 2, we could prove that this version, the algebraic version, and the actual not Floer homology is isomorphic. And I have 1 more minute. So, of course, there are 2 other things you want to do here. Work out the general case. This is a work in progress. There's a more complicated algebra that encodes the corresponding degeneration problem. But I still think if I could go back to this question a little bit, so that we have it on the board if you have questions. This kind of reverse engineering question in its full glory, I think it's still a fascinating problem because Kauffman states are so simple. And you would expect that one eventually will come up with a different, simpler kind of chain complex on Kauffman states with these kind of properties. So perhaps I would stop the lecture now, and I'll try to answer questions.
You can take some more minutes if you want. You have some time still.
I do? Okay. So, maybe a few things. So, algebras like this, they're not exactly these, but very similar algebras have been developed by Lipschitz, Oswald, and Dylan Thurston. They study decompositions of C manifolds along a genus G surface, and they worked out a computational gadget for Higgs homology, the head version of Higgs homology. They're also working on the minus version. The degeneration here are very similar in some sense, but since we are degenerating the knot, the kind of, I mean, there are some differences. One of that which didn't come up in the original thing is that there are different ways to deal with boundary degenerations, which is the main problem to trying to generalize this construction to the full not-Floer homology version. But there are also some things that are very similar. There are algebras that coming from one direction, and there are some kind of dual algebras. And you can try to understand the duality between them by looking at very simple kind of Higgs diagrams, okay, partial Higgs diagrams. And however, this poses some questions, and the boundary degenerations are something new that we had to deal with. In some cases, in the cases that where we have these B algebras that are mentioned earlier, there are some issues with these boundary degenerations, so there are different ways to resolve them. One way to do that is to enhance these algebras with some other generators whose differential. Basically, we try to go through these regions once. So, so this is set up for the easier version. In fact, it's set up in two different ways. One is one is good for the u equal to 0 version, and other one for the u times v equal to 0 version. However, when you want to do the general case, maybe let me go to a little bit to the general case. You end up with a more complicated algebras, and we worked out this Pong algebra, which there is a paper already which you can read if you want. And maybe just one more thing I wanted to mention. So there are similar things in this algebra, the original one. There are some integers you can associate. These are the weights. There is some differential on them. This is this crossing number. And maybe just at the end, some equation that I wanted to talk about. So the main difficulty, the reason why these are more complicated, and why this is a work in progress and not yet a theorem, is that the corresponding invariant that you associate to an upper projection, so take the knot projection and take a line and take everything that above this. Here we see the very simple example, like imagine like a knot which has two, so this is where the knot starts, and then could be really complicated below. But you also have to understand some object to lying above this line, because it's an inductive process. And the corresponding D structure is something when D square is not quite 0, unfortunately, but it has something called curvature. And the curvature has two parts. Some parts are corresponding to, like this point is glued to that, 1 is glued to 2, this gives you u1 times u2, 3 glued to 4, that gives you this u2 and u4. And this is in itself would be okay. There is this more complicated omega part, which is some algebra element that tries to go through this whole region. And this is the part that makes this kind of computation not as local as our earlier construction. And this, I guess, what we still have to understand a little bit better. So maybe I actually do stop now in case you have a question.
Okay, thank you very much for this fantastic talk. Are there questions, comments to the speaker? Okay. So it would be great if we can have your slides that we can.
Sure. I can
Yeah.
send them to you.
Surely.
Just send me an email because I may or may not have your email. I'm not sure.
Yes, I will. Great. Okay. Sorry, I should stop. I should stop recording. Sorry.